Hello. Well, looks like we can get started. Welcome back. I'm glad you're able to make it in today. Well, for today's class, I don't have a ton of announcements. Pretty much they're all right here as we can see them. We're in the very last section right now, section 11.1, distances and circles. Also, we have our very last quiz, quiz number 12. This one's going to be about solving the quadratic inequalities, the second to the last section. And just a reminder about the final exam. There was an email that came out just a few hours ago from the math department about the note card that's permitted on the final exam. So on this final exam, I wish I got this information a little bit sooner, but they just released that this final exam is open notes in the sense that you're allowed to bring one 4-inch by 6-inch note card, both sides. It's allowed to have things like formulas, definitions, and that kind of stuff. The math department notified me that it can't contain the examples and solutions of problems. So it'll be things like the quadratic formula, vertex formula, and that kind of stuff. So I would say a good idea for preparing for the final exam is work out the 4 by 6 inch note card first. Make sure you have information on both sides, and that'd be a good starting point for studying for the final exam. So it's a closed book calculator, it's open note card, and a calculator will be required for the final exam. I'll probably send this information out again as another reminder just through the Canvas inbox system to the course when we come back next week. And when we come back next week, it'll be just reviewing the sample final exam here. Well, any last questions at all before we get started? I do not drop the lowest exam score in this class, unfortunately. The math department has pretty much control on all those kind of extra credit opportunities, and they don't allow me to drop an exam in this class. Any other questions at the moment? Okay, well, we have just one last section to get through. Let's start working in 11.1, distance and circles. We did do one problem last class at the end of Tuesday before ending, but just as a review, as far as the distance formula goes, this is it. That's the whole formula. The distance between 2 points in the xy plane is kind of a complicated looking thing, the square root of the difference of the x values squared plus the difference in the y values squared. But the logic behind it, we spend some time on this page, is really when you draw 2 points, if it's a slanted angle like this, the distance formula is really just using Pythagorean's theorem. So Pythagorean's theorem, distance is the hypotenuse, and we can write out the distance squared equals this leg squared, x2 minus x1, plus this leg squared, y2 minus y1. So really, the distance formula is a fancy use of the Pythagorean's theorem. And all it really gives us is a quick way to calculate the distance. It takes the square root of this side, so that's why the square root's there to solve for the distance, and allows us to find the distance without even plotting the points if we choose not to. Using the distance formula can be tricky. It's really just kind of an exercise, a big exercise on using a formula and then order of operations. So when we're working through this, a couple things that we mentioned are easy mistakes to make are you have to definitely have parentheses around your negative numbers because the square of -4 must come out as positive 16. And that's what this information is all about over here. If you write down -6 squared like this without parentheses, you really get to -36. And this is dangerous, especially in a calculator, you can imagine. If you put all this in the calculator without parentheses, it'll give you back the wrong number. The second danger is you are still following order of operations here. We have to add 16 plus 36 to get square root 52. It's tempting to take the square roots individually, but as the example on the right shows, the square root of 16 plus the square root of 36 gives you 10. But when we follow the order of operations, we get the square root of 52, which is different. So we can't break the square root across addition or subtraction. Then the last thing that kind of makes it tricky is we still have to simplify it. So going back to chapter 8, we factored 52 as 2 squared times 13. And so now we know the distance between these two random points, 1, -6, 5, 0, is exactly 2 root 13. It's the length of this line segment going this way. So we'll take another look at this for the sake of practice on a different example down below. So here's our new set of points. 6, -2, -3, -5, all of them negative. Looks like we'll have to be careful with the signs as we go through this. Good way to start off is just labeling the values. This is x1, y1, x2 and y2, then just write down the formula. Distance is going to be the square root of differences in the x values, so x2 minus x1 squared, plus the difference in the y values, y2 minus y1 squared. And what we label these as turns out to be not actually relevant in the formula. If you call this x2, y2, and this x1, y1, it'll look different when we go to plug in the numbers, but we actually get the same kind of value. Similar with the slope formula as well. So after writing down the formula, this would be a good formula to have down just as extra reassurance for the final exam. This could be on the 4x6 note card. This becomes the square root of. Now we're just going to the numbers and plugging them in as we go. So x2 is -3, minus x1, -6. We have to deal with double negation, so extra parenthesis there to be extra careful. Then plus, extend that bar, y2 to the -5, minus y1, which is -2. Square that result. And now once we survive the order of operations on all this stuff, we'll have the distance between those 2 points. So let's first start with handling the double negation. First parenthesis is really -3 plus 6 squared. The second parenthesis contains really -5 plus 2, then squared. So now going down each one of these in turn, this is really just a 3 squared plus -3 squared on this one. Both result in 9, so this is 9 plus 9. So now we have square root 18, but square root 18 also simplifies. We can rewrite this as 9 times 2. I guess we could have done that as well. 9 plus 9 is just 2 copies of 9. Jumping down to this step, we can factor this down to the square root of 9 times the square root of 2 and get 3 root 2. So distance between these two random points is exactly 3 root 2, essentially by Pythagorean's theorem, but we jumped to the punchline. This square root gives us the distance in one go without having to actually draw a right triangle. We did it. That's 2 good use cases of the distance formula. Any questions with either version? Okay, really the major reason the distance formula is here is the next topic we're going to look into is all about circles. Circle seems like kind of a weird topic to end the course with as a last section. It's important because equations of circles will come up if you're taking more math. It can come up a little bit in college algebra under the so-called vertical line test, but really the bigger use of this is right after college algebra. Nowadays we call this pre-calculus 1 rather. Pre-calculus 2 is going to be trigonometry, which is all about circles. So this is kind of a tie-in with what we did before. Completing the square will come into play. So we'll use that a little bit, but it's just a helpful topic for other places in other classes. So first, here's the equation of a circle. The equation of a circle in standard form has 2 important features. The center of the circle will be at HK. And if the circle is equations in standard form, two squares have been complete this time. We have x minus h, y minus k. So from the standard form to the center, just like with the vertex formula for quadratics, we're just taking opposites. So these values for both h and k are opposites. The radius r appears on this side as a r squared. So this is the equation of a circle in standard form. It becomes not standard form the moment you square this out, combine your like terms. But in this form, it's nice because it's revealing two things, both the center and the radius. So to go from the equation to the center, we're taking opposites on both of these arrows. And also notice that there's a power 2 here as well. So that means if you want to get the radius, if you're going this way, you're taking the square root. If you know the radius r and you're putting it in the equation, you'd be squaring it. So the direction you go depends on the operation you take. To see why this is the equation of the circle, I've mentioned it ties back with the distance formula, and here's what it looks like. Let's say our circle is centered somewhere in quadrant 1. This will be the h value. This is the k value. So this is not a point on the circle, but rather just its center. The circle itself I'll draw in black. And this is kind of challenging, drawing a perfect circle. So we'll use our imagination a little bit on these notes. That's not too bad. That's kind of shocking. That's a decent circle. It has a radius r, but the radius is just the distance from the center to the perimeter, or the circumference of the circle. So if we go from here to here, just one random light segment from the center to the perimeter of the circle, the outer edge, this distance here is the radius r. So we have coordinates here, hk. Over here is just a random coordinate. It's some coordinate on the circle. We could call it, just say, an xy. So this equation somehow gives us the equation for this black band, a perfect circle centered at r with, centered at hk with radius r. It's helpful to see how this circle comes into play, why we're concerned about the distance formula, but that's kind of the trick with this. The radius is the distance. Anywhere we go around this circle, the distance between any point and the center is the radius r. So if we were to use the distance formula, we are really just finding the radius r. And this is what it would look like. Let's write this out just for the sake of tying together the concepts. The distance formula says r, our radius, which is just a fancy distance, is going to be equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. All I've done so far is just write down the equation of that circle. Let's write again, fill in the points. And we do have 2 points. We have a center, and we have another random point on the circle as well. Let's see if we can color code these. So for the x and y, I'll think of those as being the x2, y2. We don't know the specific value, so I'm just going to substitute x, y in those spots. But for the second point, the center, hk, that's the distance we're computing for the radius, we can think of that as an x1 and a y1. So now substituting in these values, we'll have x minus h squared plus y minus k squared and that's pretty much it. This really, just as it stands, is the right equation of the circle. But for reasons unknown, people decided on the distance formula, we wanted square rooted so we could get the distance out. But if we're dealing with the equation of a circle, people took this formula right here and just squared both sides. I guess it makes it look less complicated when there's not a gigantic square root symbol on here. So if you square both sides, you get that r squared equals x minus h squared plus y minus k squared. And that's our equation of a circle in standard form. The only difference now between the equation we just derived and the one above is just that r squared is isolated on the right-hand side versus the left-hand side. But it doesn't matter what side you write r squared on. Usually we'll write it out this way. But either way we look at it, that's our equation of a circle. Just an ordinary consequence of the distance formula, but the distance formula was a consequence from Pythagoras' theorem. So this thing we get is just a extension of Pythagoras' theorem to build the curve a circle. The only thing that's required is the radius has to be non-negative. If the radius was 0, well, you're just looking at a point. There's really no circle there. And a negative radius doesn't make any sense whatsoever. So we're only going to deal with a positive radius when we work through the problems and these notes. Some of the problems are really just quick plotting problems, determining what the center and radius is through the standard form. And then the next set of problems we'll look into are a little bit trickier, where we're going to be given an equation, not in standard form, the nice form we see here. It'll be our job to fix it, complete the square twice, and determine the center and radius. So let's give those a try next. So here's the standard form for the equation of the circle, just copied down again. Here are the things that we were highlighting, the various features. First thing we're going to do in example 2 is just find the equation of the circle and then graph the circle based off the given information. Let's hide some of these as we're focusing on the first one. So this one tells us to start out, the center of this circle is at 5, -3. It has a radius of 2. So to find the equation of the circle, that's not too bad. We'll write it out in standard form. All we need to do really is plug in the information. So here's how it goes. It'll be x. If we have a 5 here, we change the sign and go to -5 squared plus y. Then this sign we also change. If it's a +3, or excuse me, if it's a -3, we flip this to a +3. So +3 power 2 equals the radius squared. So the radius squared here is probably the easy thing to miss on this one. The radius of 2 goes here, but we also have to raise it to power 2. So one extra step. All we've really done is flip the signs of both of these. So it's now -5, +3, and then we square the radius. So now our equation just becomes x minus 5 squared plus y plus 3 squared equals 4. Common things to forget when you're writing down this equation is it has to be a power 2 on both the term involving x and the term involving y, and there must be a plus in the middle. Without the plus, we get some other weird random equation. Last thing to do is graph it, but we could have made that our first step. Graph the circle is just based off this information, knowing the center and radius. So a quick graph would look about like this. The center is at 5, 3, so let's go right 5, down 3. So there's our center point. The radius is 2, and so it's kind of tricky to get a nice by hand plot. But one way you can do is just give it a couple points. If we go up 2 from the center, then since the radius is 2, that would be a point on the graph. We go left 2 from the center, that's another point. And you don't have to get too wild here. 4 points would be fine, but if you can draw a circle through these 2 points, that should do the job. So let me give it a try. That should work. It's a little unbalanced. Doesn't look like the blue dot is the direct center of this circle. Doing a perfect by hand sketch again is really, really tricky. But let's let this one stand just to kind of convey, if you're doing this one on, say, the final exam, it doesn't have to be perfect. If I can tell where your center is and what at least 1 or 2 points are, then I would give full credit. We won't lose points due to artistic talent. So that's our first one down. We wrote down the equation of the circle, plotted it, and we'll try this a couple more times before we go in the other direction. Any questions first, getting through this one? Okay, let's try this out again. This one's a little bit tricky because, well, it's simple for the center, but sometimes when you make things kind of simple like this, 0, 0, it has a habit of being just a little bit more tricky. Also, the radius is not an integer this time, it's 5 root 3, so we have to be careful when we go to square that value. But every one of these starts off essentially the same way. If you're writing down the equation of the circle in standard form, then you can just start by writing down exactly what you see here. X minus h squared plus y minus k squared is equal to the radius squared. Then we just plug in the information based on what's provided in the problem. This will become x minus 0 squared plus y minus 0 squared again equals 5 root 3 to the power 2. Well, we followed the instructions verbatim to the letter. H is 0 and k is 0. So now we have to take one more step to just simplify these two terms involving both x and y squared. X minus 0 squared is just x squared. Y minus 0 squared, likewise, is just y squared. Here's the part where we need to be a little bit more careful. Squaring 5 root 3 means we square both factors. So this is really 5 squared times the root of 3 squared. So now it's x squared plus y squared equals 5 squared root 3 squared becomes 25 times 3, since root 3 to the power 2 just gives us a root 3 back. So the whole thing here just becomes a 75. So x squared plus y squared equals 75 is the result we get. It's helpful to know that if you see just x squared plus y squared, that automatically implies the center is right at 0, 0. 75 is kind of a scary number to deal with when drawing a circle. It doesn't say the radius is 75. The radius is 5 root 3. So whatever goes here, you square root it to get the radius. Much like in this problem with the 4, when we square root this, we get the correct radius of 2. So now we have to plot this thing. It's kind of awkward because of the radius being an irrational number. So this is a good use of the calculator. Radius of 5 root 3 is to the nearest, let's say, 10th. 5 square root 3 is really 8.7 after rounding. And that's enough information to get started on the plot. So let's put that down next. So we're centered right at 0, 0. Then we have to go to 8.7. So let's plot 9 tick marks. We'll have a point roughly here. That's going to be my best approximation of 8.7. And let's go with the strategy of putting down 2 points. So there's 9 tick marks going that direction. You know, they don't look like they're an equal scale. So let me try one more time. That's closer, maybe. So 8.7 right above here, close to the 9. And now circle between those 2 points in black will look about like this. Not perfect, but that'll do the job. Better than my other one that didn't quite even look like it has a the right center. So this would be negative 8.7 on the y-axis, negative 8.7 on the x-axis. If you tie down 2 points, that's good enough for me. I'm drawing the circle. So this circle, again, is equation x squared plus y squared equals 75. Well, any questions or comments so far, getting through these two first sketches? Okay, let's try one more, and then we'll change gears to the other kinds of exercises. Lost the enter button, there we go. So this one has center 6, 4, radius 9. So writing down the equation of the circle, this will be x minus h squared plus y minus k squared equals radius squared. Our h and k value is the 6, 4 given. Value for radius is the 9, so we'll have to square that. So this becomes x minus 6 to power 2 plus y minus 4 to power 2 equals 9 squared. So that's all the information substituted in. Typically, we have to simplify our answers, so let's square the 9 for 1/3 line. If we saw that coming and you just wrote an 81 there, that would have been just fine. So the equation of this circle is x minus 6 squared plus y minus 4 squared equals 81. Now we can go ahead and sketch this one pretty rapidly. Again, we could have started out by sketching it. So radius is 9 and the center is at 6, 4. Means we're really just emphasizing quadrant 1, it looks like a whole bunch. Let's put down the center first. So we're at 6 here, up 4. And here's our center point. Now, because the radius is 9, it's kind of annoying. We need to go 9 tick marks to the right of 6 to get another point. So that'll take us to 15. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's 1 point on the circle. And from here, we could draw the entire circle if we so chose. Let's put down 1 more point. To go from the center up 9, we hit the circle again. So from 4, let's go up 9 more values to get to 13. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now 13. So directly up from the center at height 13 is the second point on this circle. And there's 2 more in the other quadrants, it looks like. This quadrant and this quadrant. But here's what the whole equation of the circle would look like. Not the equation, but rather the curve. To the best of my ability plotting it, this one's kind of looking like a potato almost, but let's let that stand. So if you did your best you can in the circle, that's okay. Try to get it through the points you plotted. Try to make the center look all right, and you'll always get full credit. I mean, really the only way you could lose a point if it looks something kind of outrageous like an ellipse. If there is for some reason sharp edges to it, then that can't be right. That's not a circle. So if you avoid those extreme cases, you're going to be just fine while I'm plotting these circles. Well, that's the standard form for the equation of the circle so far. Next topic we're going to do on these notes is, in a certain sense, going backwards. We want to be, once we see an equation like this, to be able to find out what is the center, what is the radius, because we notice really plotting this is just all about getting the center and radius. So example 3 is less about plotting the circle. We can imagine it in our mind once we know what the center and radius are. So it's all about finding those center and radius values. And because it's still a new topic, let's carry this down to help us out. Really, it's still all about this, the standard form for the equation of a circle. So if we can take this equation and somehow force it to look like this, we'll know the center and we'll know the radius. We'll just keep in mind that whatever goes here conveys back to the center by taking the opposite of the values, both h and k. And the radius we get is found by just taking the square root of whatever the r squared value is. So just for the sake of tying those thoughts together visually, we once again go here to here by opposites. And this time we're going in a specific direction. We have to take the square root, whatever the value r squared is, to get our radius r. So this one's not too bad. You might recall that if you see an x squared y squared, automatically the center is 0, 0. But just showing how it works up here using the standard form, you could take this and rewrite it as x minus 0 squared plus y minus 0 squared. That's a nice strategy because it reveals the h and k value equals 16. You could write this in as 4 squared if you so choose. If you go this route, we can now say that the center is at coordinates. You take the opposite sign, but -0 and +0 have the same numerical value. It's just 0 any way we look at it. So center is at 0, 0. And the last thing, the radius, r, is the square root of this value, 16. So we get just a radius of 4. So that's what the process looks like. The squares are complete on this one. X squared is just really x minus 0 squared, and same from y. So if you have an equation of the circle where the squares are completed, this work is usually pretty fast. Really, you're just stating what the standard form of the equation of the circle would have told us in the first place. So part A is tricky because we had to kind of force it to look like the standard form by including the -0 to reveal the center 0, 0. Part B is maybe less tricky. That's a nice completed square for both x and y. We can just immediately state both center and radius. It'll be based off these values for center. The center for this is going to be equal to, we take +5 and -11. So again, no matter how you look at this, one thought you might make is to get it to the standard form, you need an extra negative sign. So you can fit an extra negative sign here, but now you need a -11 to handle the double negation to get back to positive. But really the clean way to think about it is whatever these values are, no matter what signs you get, you always flip the signs. -5 to +5, +7 to -11 is a great rule, a great way to think about it. Last thing is the radius, but notice this one takes a little bit more computation. That's not the radius, that's the radius squared. So we have to square root it like before, square root 27. But the moment we write that, we have to also simplify the square root. 27 is 9 times 3, so this is really the root of 9 times the root of 3 to give us 3 square root 3. Now, if you squared 3 square root of 3, you'd get back to a 27. So those are two routine problems. They're not too bad to do. But suddenly part C and part D are way worse. Everything is completely scrambled here. We don't even have a number on the right-hand side, like we expect in the standard form for the equation of the circle. No squares have been completed because there's an x squared and a 4x. There's a y squared and a -8y. So this one needs an extra strategy to get through. Really, we're going to complete the square twice to survive this problem. It's been a while since we completed the square. We did it a little bit to get quadratics back to vertex form. But I think a good warm-up exercise for us would just be, let's do this problem from way back and say, I think this was a while ago in chapter 9. We want to solve equations by completing the square before the quadratic formula. Let's do one here now, just for the sake of, it's a good review problem. It's great for the final exam review. but also loops back into this where we have to complete the square twice. So let's call this one a warm-up / review. Instructions will be to solve by completing the square. And the equation we'll solve is 3x squared plus 27x minus 18 equals 0. Once we see how to complete the square on something like this, we can co-opt that strategy in part C, complete the square in both variables, and get that back to standard form. So we'll pause on part C and return back to this concept from back in the day. One of the very first things we mentioned in the step-by-step guide for solving by completing the square is we want the leading coefficient to be a 1. Down here, that's automatically the case. So we have 1 on both x squared and y squared. But up here, we can divide the whole equation by 3 to get to that step. So start by dividing by 3 here and here. We get x squared plus 9x minus 6 equals 0. The next strategy we need for completing the square, and we'll use the same strategy down here in part C, is we want just the variable terms on one side and the constant terms on the opposite. So we'll add 6 to both sides. Left-hand side is just now x squared plus a 9x. We go plus and leave a little bit of space because we're going to modify this equation. Here's 6 added to the right-hand side, and plus, just because whatever we do to the left side, we have to balance it by doing the same thing to the right side. Now, next thing we do is, if we're completing the square, the major formula we're using is b divided by 2 squared. Well, it's kind of a nice formula. If you have a leading coefficient of 1, b is just a 9. So this becomes 9 divided by 2 squared. So here's our b value for 9. That plugs in right here. So 9 over 2 squared is going to be 81/4. Kind of an inconvenient number, but we'll handle it. So if we add 81/4 to both sides of this equation, we'll have the square completed, just like the square was completed on x minus 5 squared or the y plus 11 squared. Let's actually center back on that just as a reminder. So we'll go plus 81/11 here, 81/4 here, 81/4 here as well. And the left-hand side is going to now factor automatically. We're factoring essentially through a formula to complete the square. We'll go x, power 2 goes here, and this 9/2 is what carries in. So whatever this value is, we drop it in, along with the sign, so plus 9/2. Tricky work is on the right-hand side where we have some fraction arithmetic to resolve. Let's do this on the margin as scratch work. Multiply this by 4/4 to get the least common denominator, and it's now 24/4 plus 81/4. 81/4 gives us 105/4. So our right-hand side here is 105/4. And now the square's been completed. The major next step we took right here to solve the equation is just use the square root property. We can take the square root of both sides. Here's where we're going beyond what we would need to do for our circle formulas. But for this, if we're solving an equation, we need to put down a value for x, square root this side, which gives 2 possible answers, a positive and a negative, which means we also have to deal with square rooting 105 and seeing if that's simplified. So let's take a look into 105. So, well, 5 definitely divides it, goes in 21 times. 3 divides 21 7 times. and that's the full prime factorization. That's actually fantastic because it tells us no primes are repeated. And so by that prime factorization, it tells us root 105 is simplified. We can't reduce that root down any bit. Root 4 we can reduce. The square root of 4 will come out as a 2. So upon taking square roots, power 2 is canceled on the left. We have just a x plus 9 halves equals plus or minus square root 105 divide by 2. All we did is square root the denominator. Still haven't solved this. We now need to subtract 9 halves from both sides. So x is now equal to negative 9 halves plus or minus the square root of 105 halves. So we did it. That's completing the square. We also did steps we don't take in this section of actually solving for x. For the problems below, we just need to complete the square twice, not solve for x or y. We're just trying to get it into standard form so we can see the center and the radius. But any questions with the major parts right here, just reviewing the formula for and strategy for completing the square? Okay, let's put this into practice. So instructions on this was find the center and the radius. And it's all been scrambled. But if we use this again, let's carry this down one more time. Using this concept again, along with completing the square, it's not too bad of a problem, really. We just had to know how in the world do you start this. So this is our end goal. The square is completed 2 different times, one for each variable, both x and y. Using the last problem as a guide, we want to put all the variables together and move the constant term to the opposite end. You also want to do a little bit of organizing. Bring the x variables next to each other. So let's rewrite this as x squared plus 4x. Put a little bit of space there, go plus, blank, plus, then start putting down the stuff for y. It'll be y squared, bring all y variables together, so y squared minus 8y. Then go plus, a little bit of space, equality. So that's where this equality came from. We're subtracting 16 from both sides, so minus 16 is on the right. But we're also adding 2 values to get this to the standard form. So we'll go plus and plus. Whatever we add to the left side, we will also add to the right side, in other words. So that starts it off. Now we have to complete the square twice like we were mentioning. But doesn't matter what the variable is, it's the same kind of idea. You take a b coefficient, you divide it by 2, and you square it. To get the right b coefficient, the leading term has to be a 1, so we're automatically meeting that condition. And the b coefficient here is a 4. So we're taking 4 divided by 2 and squaring it. That's just 2 squared, 4a4. That goes back up here, we go plus 4. But whatever we did on the left-hand side, we also do on the right-hand side. So plus 4 over on the other end, here to balance it. So that's the vertex formula. My claim now is that that part right there is a perfect square, and we'll factor it on the next step. If we can do that once, we can definitely do it twice. We just do it for the second variable, y. It's the same exact formula. Take b over 2, square it. The b coefficient has changed this time. The b coefficient is negative 8. So that goes in here. So this becomes a negative 4 squared for positive 16. And that positive 16 just gets fed back into this part of the equation. We add it to both sides, so don't forget to add it to this end as well. You'll notice you forgot possibly to add it if the right-hand side came out negative. Remember, the value for the radius has to specifically be a positive value. Well, by using that plus 16, we can now associate these last 3 terms on the left-hand side This is also a perfect square. So let's do the factoring step next. So power 2 here becomes a power 2 on the outside. And this 4 right here becomes a plus 2. Which is the same as that 2 you see there right before you squared it. So you maintain the same sign, plus to plus. You could take the square root of this 4 and make it a 2, or this value right here before you squared it is always what goes inside. If you imagine foiling out x plus 2 times x plus 2, you do in fact get x squared plus 4x plus 4. Then we just do it all over again. Go back to variable y. Y goes here, power 2 on the outside. And this entire value, negative 4, just drops in right here. This will be minus 4. It maintains this sign. So if there's a negative here, there'll be a negative down below. But the cleanest way to see it is if there's a minus 4 here, the whole thing goes in. And likewise, FOIL y minus 4 squared, and you would get the negative 8y in the middle and a positive 16 on the end. Almost there. Last thing to do is just to combine these like terms. It results in a value of 4. So we just about have it. This is now in the standard form for the equation of a circle, which means if we use these two pieces here, take the opposite signs, we now have the center as well. Any questions before we go to state center radius on just getting to this stage? Okay, well, here's the big punchline for this one. The center is going to be located at coordinates. Take the opposite of this value, so negative 2. Opposite of this value, so a positive 4. And last for the radius, this one's tricky because what goes here is not the radius, it's actually the radius squared. So to get the right radius, take that 4, put it into a square root, and that tells us the radius is 2. At that stage, our work is done. This one is a complicated circle, the complicated equation for the circle, because someone took this nice form, multiplied out x plus 2 squared, y minus 4 squared, and essentially just scrambled the whole thing to get to that line. Completing the square twice reveals all the important facts about this circle. So if we had to plot it, it would be a really fast process. We'll try it out again just to get a feel for how this goes. Here's our second version. So this one will be the last question for the notes. That's kind of exciting in a way. This is the last topic and the last problem for the entire course. X squared plus y squared minus 12x plus 12y plus 71 equals 0. It's hard to tell if that even is an equation of a circle or not. But if we go to complete the square in both variables x and y, we'll know right away. First step is really an organizational step. We bring x's together. So x squared minus 12x. Put a little gap so we don't have to write too many new lines. Then bring y's together. Y squared plus 12y. Go plus, another gap. Subtract 71 from both sides. Then we add two more things just like before. So whatever we put here, we put on the opposite end, and same for the value on y. And really, it's just a matter of completing the square twice once more. So let's run through this again. The big formula is b over 2 squared. For variable x, that's going to be negative 12 over 2 squared, which is negative 6 squared. We save that number because that's going to be used again in part of the factorization. But for now, we do have to square it to get the 36. We copy it both here and here. Then associate just to help our eyes see that this is going to be the first part, kind of like the x plus 2 we had above. Then just rinse and repeat. Do it all over again. Now for the variable y, b over 2 squared. This time is a b coefficient on this one is 12, so 12 over 2 squared, which means we have a 6 squared. We save that value for later, just like before, but this comes out as 36 as well. So 36 goes both here and here. Last thing to do on this line is associate both sides like that, and we're ready to start factoring. So it's kind of a weird problem where in this one line, we actually did a whole bunch of steps using one formula, two different ways to get those magic numbers 36, 36. And now for our second big step, we just factor. Here's what it's going to look like each and every single time we do this. We have x plus or minus something squared, and same for the variable y. The negative here strongly suggests it's going to be a negative sign. But the negative 6 right here, if you wrote in that step, absolutely confirms it. A second way to think about this is the negative here definitely copies down, and you take the square root of 36 to get that 6 down as well. I like going this route. It's just the negative 6 right before you squared it, I think is a cleaner way to see it. So let's put an arrow on this one. Trying to avoid too many arrows like on the last part. C example above. That seems like a lot of arrows. But on the next one, this 6 is going to come down as a plus 6. We know it should be positive because it has to maintain that middle sign positive as well. And square root of 36 is also 6 as well. Last thing to do, this is the moment of truth. This is a real circle if the right-hand side comes out positive, but it does. 36 plus 36 is 72 minus 71 gives us a positive 1. So now we have an equation of a circle in standard form. We can write out the center. Center is going to be found by taking opposites. So opposite of this value gives us positive 6. Opposite here will give us a negative 6. And finally, the radius of this circle, this one rare time is actually 1. But I think it's a good idea to write this down just for muscle memory, to remind yourself on exams. The radius is the square root of whatever you see on that red dot. It just so happens this one and only one time, square root of 1 is itself 1 again. So this weird equation was just a fancy way to say circle centered at 6, negative 6, radius 1. I never would have been able to tell that just looking at these numbers. It's kind of random, it seems, how this information comes down here. But completing the square shows us it's not random, it's just a process. Well, any last questions at all with the last problem on these notes? Okay, well, it looks like we finished a little bit earlier today. We're officially done with the entirety of the course content, so congratulations on getting through it. That's a great feat. And that means for when we come back next week, we're going to spend the entirety of Tuesday, the entirety of Thursday, just talking about and reviewing for the final exam. I have several different documents. I posted versions 1 and 2, which are similar to what you saw in exams 1, 2, and 3. But this is a new mashup of problems as well. Version 3 is just some more paper problems that you can take a look into with solutions as well. There's also a practice final exam in the Newton homework system, split into 2 parts, so it doesn't feel like one humongous exam. But this sample final exam is the one we're going to look into in class. We open it up to just take a peek. It gives us a good feel for what the real final exam is going to look like. It is a little bit longer because it's trying to cover a lot of bases for a practice exam. But this will give you a good sense for what do the questions look like, how is credit awarded on the actual real final exam. Now we'll be going through this document when we come back on Tuesday's class. So we'll end a little bit earlier today. Looks like we got through the course content a little bit faster than I thought I would. But any last questions at all before we call it a night? Yep, you bet. Well, have a great night. If any questions come up while you're studying for the exam over the weekend, don't hesitate to write. I'll be happy to help. Otherwise, we'll be back to this on Tuesday. Have a good one.